Okay, so this is the start of homework two. We will begin by deriving the three governing equations that are involved in the McCabe-Thiele diagram, that being the rectifying section, the stripping section, and the Q line. So to start this video, let's start with drawing out a McCabe-Thiele diagram. And just going to draw it out. So to begin, a McCabe-Thiele diagram is a graphical method of representing the liquid and vapor mole fraction within a binary mixture in a distillation column, assuming constant heat or no differentiation in heat of vaporization between the components, thereby allowing there to be equal molar flow, and being able to say that if there's 1 mole of vapor going down the distillation column, then that means there's 1 mole. If there's 1 mole of liquid going down the distillation column, then there's 1 mole of vapor going up it as well. So out of the McCabe-Thiele diagram, it's written out. It's written out something like this. So make sure you can see it. Okay, you should be able to see it. Okay. So you have your line here, this straight line here, which represents your x equal to y line. And then you have a vapor equilibrium curve that you will be able to use when defining your rectifying and other governing equations. So within this McCabe-Thiele diagram, like I said, there's three governing equations. The first one being the rectifying equation. So that essentially starts here at our distillate composition. Call that XD right here. So yeah, so you start your rectifying section. At that point, we'll get into why exactly we start at that point later on in the video. But essentially from there, you're able to derive an equation from the mole balance of the distillation column, and you're able to figure out what the slope is of that equation and draw a line from it. And that nowadays doesn't seem too intuitive as to why that'd be important for us, because a lot of these calculations have been digitalized, but back in the day, when there was no calculators, this was golden for engineers to figure out what compositions are being found on each tray at certain reflux ratios or certain feed qualities. So yeah, so you start here with your rectifying section, and then the next section that you would start with is the stripping section, and that usually is started at your bottoms composition, which we call XB. So starting at XB, you're able to derive another equation via the mole balance in the distillation column, giving the slope of that stripping line equation. So from there, you're able to draw out a line that intersects with one of the points on the operating line. And at that point, you're able to draw out the third equation, which is our Q line, which represents the composition, or which is a representation of the slope coming from our feed section of the distillation column. And that is typically drawn right in the middle. And the slope of this line is determined by the feed quality, or whether the feed is a vapor or a liquid, which we will get into later on in the video. But so you're able to draw that line here, and then that line is usually started at our feed composition, which in this video we'll call Z. So this is just an overview of what the McCabe-Thiele diagram is. Now we'll get into drawing out the mass balances on our distillation column and deriving the equation expressions. Okay, so starting with our rectifying section, we define that as everything above the feed section of the distillation column. So what that looks like visually is at the top with our condenser, right? And then let's say for simplicity's sake, we'll say there's just one more tray below it. All right. So here, this first tray is going to be sending up a vapor with a flow that we'll call V, right? And then this condenser will be sending out two flows. We'll be sending out the distillate flow and then the liquid flow that's being refluxed back into the column that we'll call L, right? So from this, we're able to write out two mass balances from the system. So first, we can write out a general mass balance, setting the inlet flows going into the condenser being equal to the outlet flows going into the condenser. Actually, as a matter of fact, let's make this two. So we can even say that LV. So to add in another fact, we can even say that the vapor flow and liquid flow going into the second tray here with this distillate column, we can set these equal to each other because we're able to say that there's equal molar diffusion occurring within the trays, and the amount of vapor that's coming up is equal to the amount of liquid flow going down. So writing out that general mole balance, we're able to say that the inlet flow we're able to say that the inlet flow is equal to the outlet flow. So we can say that the vapor flow going in, let's say in this case for the condenser, the vapor flow going in to the condenser is equal to, yeah, you can see, okay. Let me try a different marker. So the vapor flow, yeah, going into the condenser is equal to the liquid flow plus the distillate flow going out. So that's our general mole balance or mass balance equation. So from that, we can now derive one for the more volatile component in this system to be able to identify the liquid and vapor mole fractions of this more volatile component in the distillation column in each tray. So the way that we do that, we just say that P, let's say Y, in this case Yi plus 1 is equal to the liquid flow times its liquid molar composition plus the distillate flow times the distillate composition. So in order to build out this McCabe-Thiele diagram, we want to be able to set or find a governing equation for our vapor molar flow. So we want to be able to get this Yi plus 1 by itself. So to do that, we can say that Yi plus 1 is equal to L xi divided by V plus D xd divided by D. So now in this part of the equation, we introduce a new variable that we're able to utilize in this distillation column called the reflux ratio. Now, the reflux ratio algebraically is written like this. So we say that the reflux ratio is equal to the amount of liquid that we're returning back into the tray, back into the column, divided by the amount of distillate that we're sending out. So if we say that we have a high reflux ratio, that means that we have a lot of liquid that we're returning back into the column comparative to the distillate that we're sending out to some other process. So here we're able to utilize that here in this equation We'll do that later on. First, we want to be able to sub in our vapor flow here. So we want to be able to sub in our general mole balance into this more volatile mole balance that we derived here. So let's make sure here. Just want to make sure it's catching this. So we're able to say that yi plus 1 is equal to Lxi divided by L plus D plus dxd divided by L plus D. So at this point, we have everything in terms of either liquid flow or distillate flow. So seeing this, we're able to we're able to use an algebraic trick to make this equation easier for us. So we want to be able to relate the vapor molar composition to our reflux ratio, because our reflux ratio is a variable that we're able to change throughout the process. So to do that, we can just divide by the distillate flow on the right side of the equation. So we just divide by D, and divide by D here. And when we do that, we get that R over R plus 1 times X, call that Xi, plus 1 over R plus 1 XD. We get that is equal to our vapor molar composition, and this ultimately becomes our equation for the rectifying section. So now that we have that, we now know what the slope of that line is. We know what the slope of that line on the McCabe-Thiele diagram is. However, we don't necessarily have a reasoning as to why the XD, or the distillate composition, is on that y equals x line. So to do that, we just the rationale through that is that because we know the slope of the equation, we still need a starting point, or a y-intercept, as we would say in algebra, to start that slope off of. So to do that, we need to make a valid assumption. And the best assumption that we can do in this point is to say that our, we can say that our xi here is equal to our distillate. So at the bottom here, we say xi is equal to xd here. So once we do that, if I erase everything here, so yeah, like I said, we say that xi is equal to xd. So once we do that, we're able to rewrite our rectifying line equation to be that y is equal to r over r plus 1, this is times xd, and then we have xd r plus 1. And here, we can see that we have two common denominators here. So we're now able to add these two equations together. And when we do that, we see that our numerator and our denominator are equal to each other. So then we can just cancel it out, and that becomes 1. So then we're able to say that our corresponding y value is equal to our distillate value, which essentially makes sense because when the vapor is going up into the condenser, the composition of that isn't changing as much. So the distillate of that should be the same. So that's how we algebraically prove that the distillate composition lies on the same point as our y value, in this case, y1. So that that is the algebra for our first governing equation, the rectifying line. Next, let's move to the stripping section. So we're going to be deriving the stripping line. So definitively, that the stripping section is anything or are the trays that are below the feed section, and we can write that out similarly to the rectifying section. This time we're going to start with the boiler though. So here we have our boiler, we have our bottoms feed here, we have our vapor feed going up. Now, something to remember here is nomenclature wise for the bottom section, we wanted to note our flows with a bar. So we say that V bar and L bar going down here. Then let's say we have a tray here, has some vapor, have some liquid going down. And then let's say we have our feed coming in here. So this entire bottom section represents the stripping section of a distillation column. And similarly, we can write out a material balance that will allow us to derive, or will allow us to get to the stripping line equation. So here, similarly, we just look at our reboiler and we say we quantify what's going in is equal to what's going out. So we say that L bar is equal to V bar plus our bottoms. Boom. Next, we want to write out the material balance for a more volatile component. So we can just say that L bar, and let's just write X. We'll just write it as X is equal to V bar Y plus B and then the X bottoms. So this is the composition of the bottoms going out of the reboiler. All right. So similarly to the rectifying section, how the rectifying section had a reflux ratio, the bottoms or the stripping section has a similar parameter known as the boil-up ratio. So we know the notation for that being VB is equal to V bar divided by the bottoms. And similarly to the reflux ratio, it's the amount of vapor that you're sending up through the column divided by the amount of bottoms that you're sending out of the column. So by doing that, we're able to utilize that later on in the equation. So now we can start to single out our y variable and get that by itself. So we can just rewrite that by saying V bar Y, or matter of fact, we'll say that, we're going to say that Y is equal to bottoms, or yeah, the bottoms minus our L bar X. That's all divided by V bar here. All right. So now, if we do a bit of substituting, we can substitute this L bar here for the L bar here, and then we get Y is equal to B X bottoms minus our VB plus X. All right. All that divided by V bar. All right. And once again, we want to be able to get this equation to be related to a variable that we're able to change, or a variable that's more of an industry practice to vary. So we want to be, so essentially we want to be able to get this equation to be related to our boil-up ratio. So how may we do this? Just divide by B. Similarly to how we did it with the reflux, or with the rectifying section equation. So we just divide by B, divide by B, divide by B, and divide by B. And here, we're able to see that this becomes, we're able to write that y is equal to 1 over VB times XB minus, right? So this becomes VB plus 1 over VB times our X. And this final equation becomes our, well then, okay, that's not very much. And sorry, make sure this is should be a bit better. Yeah. So essentially this becomes our governing equation for the stripping section. And similarly to the rectifying section, we need to be able to have a starting point or a y-intercept for this equation. So the best guess to doing this is just by setting our x variable here to be equal to our bottoms variable. All right. And once we do that, we're able to see that we have a similar situation where this just becomes xb, and we have common denominators, right? And then when we combine these two expressions, or when we combine these two together, we're able to see that the ones here cancel out, and we're left with VB over VB, which equals to 1. And we can just say that our Y is equal to our bottoms composition. So this essentially is the algebraic reasoning as to why we're able to say that this XB composition lies on that 45-degree line. All right. And finally, we'll get into the third component, the third line on this McCabe-Thiele diagram, which is the Q line. So the Q line, that is representative of the feed composition and the liquid and vapor streams going in and out of that feed tray. So here we'll draw out our feed tray here. All right, so this is our feed tray. And then we have a feed with some flow rate, we'll call F for our feed. All right. And then starting above the feed, we have everything that's in our rectifying section. So we have the vapor flow. We have the vapor flow going up from the feed. We call that V. And then we have the liquid flow coming from the tray above. We call that L. Right? Then from the stripping section, we have the vapor that's coming up. We call that V bar. All right. And then we have the liquid coming down from the feed tray. We call that L bar. Okay. So essentially, with this, we're able to draw out another material balance here. However, what we can do now is just combine the two equations that we derived earlier, the rectifying and the stripping section equations, combine those two together to form our governing equation for this Q line. So let's do that. Starting with the rectifying section, that was y is equal to, I believe it was r over r plus 1. I believe that is, this is x, I believe, plus 1 over r plus 1 xd, right? All right. Actually, no, I'm going a little too far, going a little too fast. So we draw out our material balances for them. So we say that Vy is equal to Lx plus our dx, right? And then we say that L bar, so yeah, L bar x is equal to our vapor plus our bottoms. All right. And then if we add these two together, we get V plus L is equal to Lx plus Vy, V bar Y, plus dxd plus Vxb. Okay. And already we can make some simplifications to this equation because if you look here, dxd plus Vxb, that essentially becomes equal to the feed composition going into that tray. So this just becomes Fz, which is our feed composition. So we can simplify that, and then another thing we can do is represent or introduce a new variable that has to do with our feed composition. So we have another variable. This is called Q. Q is our liquid fraction, is our feed liquid fraction going into the tray. So this basically represents how much of the feed is a liquid. So if the feed is half liquid, half vapor, then Q is equal to 0.5. If it's a saturated liquid, then Q is equal to 1. If it's a saturated vapor, then Q is equal to 0. So why this becomes important is we're able to identify the amount or the residual amount of vapor and liquid that goes into the rectifying or the stripping section. And what I mean by that is essentially we can write out equations for how much of each excess of each phase is going into each section. So for example, for the vapor, we can say that the vapor, right, that's going to be equal to the V bar, right? So that's going to be equal to V bar plus the amount of vapor that's being brought in by our feed. So that would be V bar plus F 1 minus Q. Because 1 minus Q, that just gets you the amount of vapor that's coming in through the feed. Similarly, with L bar, we can write out how much residual liquid is being brought in from this feed by saying that L bar is equal to our liquid that's coming down from our rectifying section, L, plus the amount of liquid that's being brought in from the feed. So FQ. All right. So once we've written those out, actually, I need to write out the compositions as well. So we add in these compositions as well. So once we're able to do that, we can now plug in these values or actually no, I was not supposed to. No, no. This is just flow rates. So now that we've done that, we can now plug these back into this overall equation that we've made here. So let's see. Yeah. All right. So if we plug these into the equation here, we have Vy bar plus F 1 minus Q times that Y composition plus L bar X, that's equal to, so that's equal to, or, oh, not L bar, apologies. So plus, so that's going to be plus, all right. What we derived here for L bar, we just plug that into there. So L plus FQ multiplied by X. And this is all equal to that entire right side. So Lx plus Y, or Vy bar plus Fz. All right. So right. Yeah. So now we can. Oh, wait, that could be. Oh, that's not what I meant to. That was not what I meant to do. So now, we can start factoring stuff out and eventually start canceling out terms and get our y variable by itself to solve for that line equation. So here you'll have v bar y here. If we move that to the other side, that cancels with this v bar here. So that cancels out with this right here. All right. And then this lx here, that cancels out with that lx there. All right. So then we're left with f 1 minus q, or yeah, y, f1 minus qy, all right, plus fqx is equal to fz here, right? Okay, so now we have that equation written out here. And if we want to get our y by itself, we just move this to the other side. So we have fqx here. That goes to the other side. And then we can divide out. So then we can divide out our f times 1 minus q. Move that to the other side. F 1 minus q. And then we just cancel out those f's there. Now we have that y is equal to z minus qx 1 minus q. Okay. So this is the governing equation for the q line. Now we just need to prove why that line can start where our composition starts. So to prove this, our y starts on the y equals x 45-degree line. So we do this by assuming that our x value is equal to our composition value. So we say that x is equal to z, right? When we do this, we get this right here. And then what we can do is we can factor out that z, which makes this 1 minus q this becomes 1, and then our y is equal to z. So that then essentially explains why we're able to assume that this Q line can start where our composition point is. So it's very similar to how we did it with the rectifying and the stripping section, and is a great method and great estimation that allows us to be able to have a good starting point for that slope that we've derived. So, yeah. But this essentially is the all the equations for the McCabe-Thiele diagram, how they're governed, why exactly their starting points are where they are, and in the next video we'll be going more into other vapor liquid equilibrium phenomena.